main question is your occasion to know everything you want to know about multi-messenger cosmology. So, Rani, it's a pleasure to have Rani here. He's finishing his PhD thesis in Vitoria at the PPG Cosmo with Valerio. So, and he will tell us about how to combine gravitational wave observation with traditional observation to make cosmology parameter estimation more efficient. Please, so you have 50 minutes and then plus questions, but I ask any time.
Okay, thank you, Ricardo. Thank you everyone to invite me. And today I'm gonna talk this work, which was the production of a gravitational wave catalog, consistently with the distribution of galaxies from the Cosmo DC2, which is a mock catalog produced by the LSST collaboration. Okay. So that's the outline of my presentation. I will start with a quick presentation of the context of gravitational waves and motivations. I will show you the methodology we developed to produce these catalogs of gravitational waves, then characterize these catalogs, but that's a kind of technical issue, so I will be very quickly here. Then I will show you some applications of these catalogs with bright side analysis and summarize some conclusions and expectations for the future. Okay.
Does everyone know what the bright side means?
Yeah.
Okay.
I will review this, but it's okay. If anyone have question, you can do it. So in the gravitational wave equation, usually we present this solution for this. Actually, this is a very approximated solution because we just dealing with the first contribution of the equations, okay? So, but the point is that solution is interesting because it shows how we could have direct access to the luminosity distance, which give us a clear window to probe the constant Hubble constant. Okay, so the bright signs and the dark signs are two different classifications of the gravitational wave events, and they are called this way because dark signs you just have the counterpart of the gravitational waves, so they are kind of dark. You don't see them with your eyes, but bright signs you have both contributions. You have the gravitational wave emission and also some kind of electromagnetic emission by kilonova or afterglow of the environment radiation. And the point is, usually it's way more difficult to have both counterparts detected. The proof of this is up to date we have detected just one, and I think there is another one in process to be confirmed or not. I'm not updated on this. And dark signs up to the
right. So one.
Yeah.
What would be the one?
There is that one. It's a dark sign in the AGN environment.
No.
Yeah, they are.
No.
Okay. So they are just one bright sign at all.
So
and
the LIGO-Virgo collaboration, they detect this bright side.
Sorry?
The LIGO-Virgo collaboration, when they detected for the first time gravitational waves from binary influence turbulence, so they detect this bright side, and so the other.
So the gravitational.
I'm very new to this, so
Of course, the electromagnetic observation was not made by LIGO, it was made by some observatory.
Yeah.
And basically, a few hours later.
Yeah, I'm not sure which telescope has detected, but it's a telescope with electromagnetic counterpart observation. And the point is, as usually this kind of event is more informative to you, if just one event you can constrain Hubble constant in this kind of precision. It's not competitive with, for example, CMB or supernovae, but it's still way better than the dark series that using 200 events, you got the same constraints. Okay. Here is it's showing the constraints on Hubble constant, and just to see how much today the gravitational waves is still not an option to constrain Hubble constant, but there are many expectations for the future and how it could be changing. So today, of course, you know, we have these detectors running and detecting new events right now. The expectations is to next years, 10 years more or less, ICE telescope and Cosmo Explorer will be built and started to work. And in parallel, you have the electromagnetic surveys working, and which is useful to detect these bright signs as well. So, given these expectations for the future, the point here is to prepare ourselves to the data that's coming for the future. We expect to detect many more gravitational waves, and we must to be prepared to deal with this data, right? So we have the idea to produce a forecast of this data, and for the cosmologist, develop techniques or methods to analyze them, and when we have a real data, we are ready to do it. So to produce the gravitational wave catalogs, we first started defining the gravitational wave parameters distributions from what we're gonna sample them and use as input in our waveform functions. Okay. So
you're telling us later what are these parameters? Are you?
What?
You're telling us later what are these parameters?
Yeah.
These parameters.
Okay. Yeah.
Okay.
Yeah.
Okay. No, you're okay.
So that table summarizes all the distributions we have used to sampling these parameters. So the big contribution here is on the position of these measures, because they are not necessarily randomly distributed in the universe. They must be correlated somehow with the galaxy distributions. And to grant this correlation, we have used a measure height density model, analytic model, calibrated with numerical simulations. Okay, and in this analytic model, the measure height density depends on the redshift naturally and the host stellar mass of the galaxy. Okay, so it means depending on the mass of the galaxy and the redshift, where is it, you're gonna have a certain value of the measure height density. And given this value, you can calculate how much measures will happen there, and then distribute these measures around this box volume there. Okay.
How are these parameters estimated? I mean, is it compared with the real data, like for the theoretical waveforms are compared with the real data, and then you estimate those parameters, or?
Yeah, actually, this work here, they have running set of simulations. Then we got this root data and then fit an analytic function and got the parameters.
They are not, they simulate physical data, not data where they can with. They say they simulate characteristics of galaxies that will give rise to binary merger. So the simulation is about the environment where binary merger occurs.
And the other distributions also are based on simulations, theoretical simulations, or studies of measured populations. Okay, So the mass distributions, the spin distributions, everything here.
Sorry, those curves are monotonic in redshift? It is difficult to understand. So do they go up and down, or they just go up, or do they just go down the redshift?
Just go down, yeah. But the way they go down depends on the mass of the host galaxy you're observing.
Okay.
For example, if you look for the more massive galaxy, which is green here, it decays faster than the lighter galaxies.
So the more massive galaxies are less metallic, so all the formation is done quickly, or no?
The way I see it is because sorry. The way I see it is that the more massive, when you go to the high redshifts, you don't have this galaxy anymore. So the matter rate density naturally decays in high redshift, but it reach a higher value when you go to low redshift here.
But they are all comparable at low redshift. Isn't it strange that the rate doesn't depend on the mass of the galaxy? Larger rate, small redshift. I mean, it depends very mildly, no?
Doesn't depend on the mass.
Yeah,
What do you mean?
all the masses, they collapse to a narrow band. See, all the lines, they belong to different masses of the galaxy, right? And those lines collapse to a very narrow band.
Yeah.
So the rate is not very much affected. So so the rate doesn't have a factor of 10 spacing between one line and the other line. You would expect naively that the rate is proportional to the total mass, but it's not. No, small redshift is not.
Yeah.
Yeah. Do you have a simple understanding of that?
Let's see. It could be an effect of the beams as well, because but then I don't know, because actually this is a continuous function, and then to plot this image, I must to calculate the function in being of mass of a host stellar mass. So I don't know if this could produce this effect as you're saying.
Okay. There just if more galaxies in another mass being compensate.
Yeah, could be. I mean, yeah, because okay, the matter rate density could increase because the environment is more probable to have these matters, but also because there are less galaxies in these properties to contribute to the matter rate density in this scale of mass as well. But I think we cannot separate this effect here. I don't know.
So the simulations that you do not provide the density of galaxy.
The what?
The density of galaxy. The density of galaxy for each mass being.
I think there is.
Yeah,
that
could be a valuable piece of information, no?
Yeah, I could use this as well to break this.
You're showing that basically all mass means contributes roughly the same, probably because there are more galaxies with smaller mass. And so they give a contribution.
Yeah, because if you look to the left plot here, in the low redshift, of course, you have more contribution from the massive galaxies here, but these contributions decays strongly when you have to write high redshift there, which is almost it's not constant, but it's more concentrated in less massive galaxies there.
Yeah, but you see on the left plot, I see that the redshift 0, I see quite a strong variation with the mass. I see variation of 3 orders of magnitude. You see, just focus on redshift 0.
Mhm.
Ah, okay, depends on the model, of course. Yes, redshift 0. Yeah, in some. So, in what differentiate the lines of this plot?
What
First line, second line.
did
BBH, okay. So BBH, you don't see such dependent on the galaxy mass, but you do see for BNS, for instance.
Mhm. Yeah. The models for the BPH and BHNS are pretty much the same, just change the parameters of the same model. But for the binary neutron stars, we have a different shape here.
The shape of what?
Of the curves, just the measure intensity. As you can see, it seems like a very uniform, but you have a peak here. But for the binary neutron stars, it's just increasing, then okay.
And Santo Liquido et al, I don't think is by seeing many body simulations.
Yeah, they have antibody simulations, then they simulate the envelope evolution of the binaries and count the measures only. This way. Yeah, so we got this count of the measures, calculate the measure intensity, then to different redshifts, to different host galaxy mass, and then we fit them getting this analytical model, right? Okay. So once we have defined the input values, now we must to generate the catalog, right? But first, we must to produce the input values for all the patch, all the tiles covering the sky. Okay, so the Cosmo DC2 is actually constrained in this region tile 0 here. It's a region of 400 degrees square, okay, up to redshift 3. And the point is the LSST will cover almost all the soft sky. So the idea was repeat this sampling in each tile covering all the region that LSST will observe in the future. So we have repeated 36 tiles here. And in the end, we have this input catalog, which gives you the galaxy ID that hosts the measure, the redshift, the intrinsic parameters, and the extrinsic parameters of each gravitational wave event. Okay. So given this input catalog, now we're gonna use it to insert in the waveform functions, okay? And for the waveform functions, we have explored 4 main waveforms here to analyze what each contribution is important for the measurement in the future, okay? So the most simple waveform here is this one, based only in modulation of the numerical relativistic, and based on this waveform, the other ones is developed inserting, for example, the high modes to get more details on the waveform shape, the spins per sessions, and the high modes with spin per sessions. Okay. Also, we have considered huge options for the detector networks here, having the Cosmo Explorers here in the United States, IC Telescope Europe, and another option of Cosmo Explorer here in Austria. But this is just a curiosity because there is no real expectations to build one there. Okay, so once defining all these observational features, it's time to produce our catalogs, okay? So we have a problem here because if you take the waveform, any waveform you have, usually you're gonna have more or less 50 parameters if you consider the precession of the spins, or even 70 parameters if you consider the tidal effects as well. So to explore the parametric space at this size, it's like I don't know how much time, but depends one day, I don't know. So we are talking about simulate thousands of millions events, and so this will be completely out of question to do it. And the idea was then approximate this likelihood with Gaussian approximation, which is the Fisher matrix here. This reduces drastically the time of estimation of the uncertainty of the parameters. Then it's make possible to do it. And in the end, we do this for all events. We have sampling in the input, and the output then presents this form with the galaxy ID here, the signal noise ratio of each one, the marginalized uncertainties. Also, we have available the covariance matrix if you need the correlations between the parameters as well. And here it says if your Fisher matrix was successfully inverted or not, because numerically in a space with 50 parameters, that's not trivial at all. Okay. As an extra work here, we have also produced a electromagnetic counterpart catalog to associate with some binary of neutron stars mergers. Okay, because as I show you, the bright signs are kind of a very variable event for cosmology. And then we decided to produce also this electromagnetic counterpart here. So to produce this, we have adopted a very simplistic methodology here. From numeric simulations again, we know that the measure of binary of neutron stars has mainly four outcomes possible, which is a stable neutron star, a supermassive neutron star, a hypermassive neutron star, or a black hole straightforward. The point is, these outcomes depends on the mass of the binary, and each one of these outcomes also produce different electromagnetic counterparts. So as we already have from the input catalog, the masses, we can estimate or predict each one of these outcomes here. And from these outcomes, we have the range of the luminosity that they're gonna produce, okay? So this plot here shows the distribution of the mass of one of catalogs we have. How these outcomes distribute in the mass as well, and how is the luminosity of these measures as well. The point here is interesting because as you can see, when you go to lighter binaries, you're gonna have higher luminosities, and the opposite happens when you go to heavy ones. And that's a mismatch between the electromagnetic counterpart and gravitation wave counterpart, because when you have a gravitation wave, when you have a binary more massive, is more easily to be detected, right? Because the gravitation wave event will be stronger. But at the same time, the electromagnetic counterpart will be fainter. So that kind of have a first explanation to why it's so hard to detect these bright signs. Okay. And yeah.
No, why it depends only on the chip mass? I would expect it to depend on the.
No, depends only the chip mass. Actually depends many parameters,
Mhm.
but we have used the chip mass as the dominated one.
Okay.
Yeah, because actually this is a point very idealized the modulation here, because it depends on the shipper mass, depends on the ejected mass, depends on the we have assumed the spherical symmetry in the emission of the kilonova, for example, which is not true. And so there are many things that we expect to improve in the next versions to get more realistic modulation of these kilonovas here. Because the most realistic way to do it is to simulate the entire light curve of the kilonova, which depends on many parameters. But again, we're gonna following that problem, which it's a problem to do it with a million events. So we have followed this this approach to do with a high number of events. Then next we're gonna do more realistic approach then. But yeah, you're right. It's not depending on the chip mass only.
But the one most likely to give a electromagnetic counterpart is helium. I mean, is it related to the classification from collapse, higher magnetizing neutron star, and so on. I mean, in that classification, which are the ones more likely to give a counterpart?
Yeah. So usually the when you have masses around 1.2 here, is more probable to have the counterpart detected. The problem is the most of binary of neutron stars collapse directly from black holes or hypermassive black neutron star that's gonna eventually collapse in black hole again. So these ones usually it's gonna be dark science. And
Because from collapse.
yeah, because and they are mostly more
Because more massive, more compact.
yeah. And that's the problem in detecting the bright signs. The mass spectrum of the gravitational waves that we can detect from these bright signs usually are shifted to more massive ones, which is the ones that produce fainter electromagnetic counterparts.
Okay.
Yeah.
So GW17 also, or 817 was supposed to produce a high magnetized neutron star, or
Sorry?
GW17 or 817. It was 1.2-ish, no? In shear mass.
Yeah, I think yeah.
So it was expected to create the remnant, a highly magnetized neutron star, or what? What was the expected remnant that?
Okay. It depends, because as you can see here in this region of the mass, you have a superposition of outcomes. This superposition comes actually because we don't know the exact form of the equation of state of the neutron star. If you assume a specific model for the equation of state, these superpositions disappear, and you have a clear limits wherein each outcome will happen. But this superpositions happens because you have a range of uncertainty there. So in this region, you don't know exactly what happens there. You just have, for example, kind of sure which it's going to happen here or here, or here, for example.
But the fact that we saw the counterpart wouldn't help you, or both the orange case and the blue case are compatible with the presence of the counterpart, like the highly magnetized neutron star and the supermassive. neutron star, they're both compatible with the presence of the counterpart.
They are both compatible.
Are they? I mean, we measured the shield mass and we saw the counterpart.
Yeah.
So apart from the collapse, all the other cases are compatible with the presence of counterpart with emission.
I'm not sure.
Now, in which region should we expect more likely the electromagnetic emission to be?
Yeah, it depends because the more electromagnetic counterparts comes from this region here.
Yeah, but because irrespectively if it's a highly magnetized neutron star or if it's a supermassive neutron star, then irrespectively of that.
No, all of them will emit these electromagnetic counterparts. The point is how faint it is or not.
Okay.
Yeah. And
Which is brighter in these cases.
usually when you have lighter red signs.
Yeah. So the supermassive neutron star is associated with brighter emission.
Usually not. Usually, the supermassive neutron star, they gonna have a fainter luminosities here. So if it's very close, you might detect them, but if it's far enough, you're gonna lose the electromagnetic counterpart. That's
Okay.
That's the point. And that's we summarize in this input catalog here from the kilonovas. And next I will talk about this kilonova in the next slide. Here it's it's summarizing some technical characterizations of the catalogs of gravitational wave catalogs now. So in the vertical axis, you have the number of events, okay? And the horizontal is the signal noise ratio. And each color of the curve, it's the network you are considering to observe the sky. So each of these lines here, it's different binaries you're considering. And from these distributions, you see clear three separations here. The first one is the network composed only by the LIGO Virgo Ekagra, the second generation detector, which presents the smaller signal noise ratios distributions. The second group is the group that is composed by Einstein telescope, but not with the Cosmo Explorer, okay? And the third one is using the Cosmo Explorer, so the more sensitive detector here.
Wait. So the integrated number are comparable?
The integrated?
No, because the y-axis is not normalized, no? It's the actual value.
Yeah.
So if you integrate the total number, is it comparable for BBH and BNS?
No, actually, it's normalized. It is no. No. Okay. And the point is that's the number of events for all the catalog input. So the number is the same for all detectors. The point is the threshold here separates which is detected and which is not.
So you normalize the total number of events?
No, it's not normalized, but the point is, for example, I have 100 input values. So these 100 input values, how distributed?
Sure.
So how distributed
They fall on the left, we don't see them.
Yeah, exactly.
Okay. Yes, but even then, it seems to see that the integrated value are not totally similar, no, for BNS or BBH.
Yeah. No.
Do you have the integrated number?
You see the cumulative distribution.
Yes. This number that you give there, are they cumulative?
Yeah. It shows only the tile 0, that one. It's not the 36 tiles, just to have
So to have the full sky, one has to multiply
by 36.
No, that's half of the sky if I multiply by 36.
Yeah. Okay, the entire sky would be 2 times 36. Yeah.
How many events do you consider per BPH?
BBH.
Year before detection, how many events do you send?
Okay, so for BBH here, up to redshift 3, because the Cosmo DC2 is limited to 3. We have for BBH around 2,000 events here in the tile 0. So you multiply by 36 and by 2 for all the sky.
And that's for the 10-year duration.
10 years, yeah. And for binary affinity stars, the colossal number is like 50,000. And binary of black holes and neutron stars, more or less more 1,030. And yeah, let's see. So it shows just the percentage of detection for each network detector. Naturally goes increasing when you increase the complexity of the network here.
Okay, no, but this is something non-trivial that you BNS overtake BPH if you have a farther range. When you look farther, like with the 3G experiment, with 2G experiment, you see more BPH than BNS.
Yeah.
Yeah. Well, with 3G, you see more BNS than BPH. This is because you basically getting to 3G, you're seeing all events, and basically intrinsically there are more BNS than BPH. So when you see all, you see more BNS.
Yeah.
Now with 2G, we see more BPH just because we can see them farther.
Yeah, because actually, let me see. I think the binary of neutron stars in the second generation here, despite they are more numerous, they don't produce a signal noise ratio enough to
Exactly.
traverse.
So each line there is some different configuration network. So what is all merger? All mergers refers to which configuration?
All measures?
Yes, you see the last two lines, you write all mergers.
Okay.
The last.
Yeah, that's before detection, right?
No, sorry, no.
That's all mergers means without the detection threshold, without considering the detection threshold. You see, you wrote all mergers.
Okay, yeah.
All mergers means that without threshold detection.
Measures without the. Okay, but what is the point?
No, I'm asking, what is all merger? All merger means without setting the detection threshold.
I know
All the mergers that happen in the universe, not those that are visible.
Yeah, that's just saying that all the measures considered in this plot is this one.
Okay.
Okay, so for example, here you have detected 28,000 events from 50,000. Still is a lot of events that has missing here. Right. At least for the binary of neutron stars, because binary of black holes, you see almost all of them. Okay. So another interesting here thing is this plot. It shows basically almost the same one. That one. It shows the vertical line, the number of events. The horizontal one is the uncertainty, the relativity, uncertainty of the luminosity distance, sky localization here, the supermass, and the mass ratio here. Okay. So the point here, we have observed that these two parameters, the luminosity distance and sky localization, which is more interesting for the cosmology analysis, they are more sensitive to the number of detectors, independently if the detector is the second generation or third generation. Then the parameters like the mass and the mass ratio. That's actually a behavior expected because these parameters depends. They are extrinsic parameters that depends on the triangulation. You can do it with the detectors, right? And these other ones depends more the track of the evolution of the frequency in the spectrum of the event. And to have a better tracking on this, you're gonna need more sensitivity detectors, which is more available only with the third generation detectors. Okay. Okay. So about the kilonova now, up to that these configurations here, using these configurations here of the catalog using Cosmic Explorer, Einstein Telescope, and LFAK, okay, with 70% of duty cycle, okay. We have counting how much of kilonovas you can detect around 10 years in the region of the sky observed by LSST. And we found that we're gonna have around 5,000 kilonovas associated with gravitational wave events. Okay. For this number, we have used the band threshold available by the LSST, okay, that they're gonna use in the future observations. And then, as you can see, actually goes up to several thousand events, more or less. But detected one by the LSST is going to be almost 5,000 in 10 years.
This is BC.
BC?
BC.
Is the prompt collapse going directly from the black hole. So you see that the supermassive neutron star is the most probable to produce the electromagnetic counterpart here, which is in that range I told you, 1.2, 1.3 solar masses. You also have contributions from other remnants, but it's way smaller. And interesting for binary of black holes and of stars, we found anything. Okay.
So why zero? What is the assumption that the zero?
Zero is because there is a relation between the mass of the black hole and the neutron star that depending on this direction of their mass, they're gonna produce or not the electromagnetic signal.
Yeah, this is because
They're gonna swallow it.
The tidal forces are not strong
Yeah.
enough to break the neutron star, it will be just swallowed.
Yeah, basically depends if it's gonna rip the neutron star before to be swallowed or not.
But this you're assuming that there is a mass gap in the black hole. Because if the black hole are light enough, this could change.
Yeah, we have used the distribution of black holes going to from now I don't remember.
Starting at 5, I guess.
In 3.
Starting at 3 already.
Yeah. So from the 3 to 60 solar masses. And still
And the neutron star, they go up to 2.
go to 2, yeah.
2 to 3, you still don't have any.
No, they have produced some events with electromagnetic signal, but still very faint.
Okay.
Yeah. So there is this effect that someone is excluded because they don't produce at all, and that ones that still is producing is very faint to be detected by at least by the LSST threshold here. Of course,
Yeah, no, but what did you assume for the amount of emission was in the VH in this case?
amount of emission.
The electromagnetic energy you see here, you get to predict that you see zero
Mhm.
because you have some estimation of the emission. What is your model of the emission?
No, actually, we have
So this is
we have produced the luminosity, the peak of the luminosity of the kilonova.
yes, but this is come from where? From where? This prediction.
Yeah, it comes from the a range of values available by simulations. So they run many simulations from different equation of states, and then they count how much is higher this luminosity for each model they have simulated, and we take this range of values and sample from them.
But this simulation, aerodynamical simulation, what kind of simulation are they?
Simulations of light curves in general.
Yeah, but I mean, they must be informed about the masses, about the physics of the neutron star, about the equation of state.
Mhm. Yeah,
So, I mean,
yeah, the details of the simulation I'm not known now.
but okay, at the end of the day, they produce an histogram of luminosity.
Yeah.
That's what you care about.
Yeah. That's why it's very simplistic way to do it. We would like to enrich this part in the future. Okay, so all the details of the production of this catalog is explained here in this paper. Okay, so if one is interesting, you can see this one. And as a consequence of this work, we have already applied this catalog in cosmological analysis of bright science. Okay, so we could do it. We are now developing analysis with dark science as well, but the bright science is kind of direct method to do it. So it was very straightforward to apply it. So first of all, we have selected the kilonovas, that's 5,000 ones, and then separate them in different subsets here, depending on the network that have detected it, depending on the constraint of the sky as well, of this kilonova. So also, we have combined it with the supernova data that we're gonna have in the future with the observations with the Roman telescope here. Okay, but the point is the bright science will constrain the Hubble constant, and the supernova data will constrain only the omega matter here. So the likelihood we have used for the bright science is kind of very simple, Gaussian one, and for the supernova also it's very well known. You can marginalize it analytically this way. And the main results we have found is these ones in the blue box is analysis that we have run only for the cosmography. Okay. For the red is the lambda CDM, and the other ones here is the extensions of it. And the first point in the cosmography analysis, we have considered only bright science in the local universe, very local, up to redshift 0.50. And we have, using only bright science, we have calibrated the absolute magnitude of the supernovae. Okay, so it's a independent calibration of the supernovae. Don't use cepheids. And we have found this calibration with a precision. This calibration with a precision a little bit better than the calibration uses cepheids here. Okay. Also, in the case of the third generation detector, if you use just the second generation detector, you're gonna have a calibration that precise. Okay. For the lambda CDM, we have constrained then the Hubble constant, and for LFK, still we don't have precision competitive with the CMB, for example. But for the third generation, using or ICE telescope or Cosmo and Cosmo Explorer, you got precisions around 0.2 or 0.4. Yeah. Again, depending on the sensitivity of the network. In the case of the extensions of the lambda CDM, you have again constraining the Hubble constant, but you don't have a high precision in constraining the dark energy parameters here. Okay, so bright science up to this point is more useful for the Hubble constant itself than the extensions of the lambda CDM. Also, again, this work is all summarized, all explaining details here in this paper. And to finish the presentation, I'll tell you that all the catalogs we have produced is available in this link here. So anyone can go there, download, and use to do your cosmological analysis, astrophysical analysis, anything. And in the end, we expect in the future, again, introduce new contributions for the gravitational wave likelihood expansion, because we have just limited it to the Fisher matrix. But again, especially in the dark side analysis, we have to consider non-Gaussianities that are included in these Fisher matrix approximations, because the constraint in the sky is deformed, and that's gonna impact in the selection of the galaxies contributions in the dark science analysis, for example. So it's a natural next step to improve our methodology here. Also, again, they incorporate more detailed kilonova modeling here, because it was a very simplistic way to simulate the peak of luminosity of these events, just to have an idea of this bright science measure detectors or detections. And in the end, also we are studying the ways to include the tidal parameters, because with this we could, for example, develop analysis to constrain for example, the equation of state of the neutron stars, right? So we're gonna be able to probe the potential of the third generation in constrain the equation of state of neutron stars. Yeah, I think that's it. And if you want to have any question, thank you.
So take your chances, since we are not many, so there will be time for everybody to ask questions. I need to ask a little bit.
Yes, so I'd like to know how you construct the catalogs. So do you first repeat the patches to cover the whole sky, and then inject the gravitational wave parameters, or like do you do everything for one patch and then repeat everything with the gravitational waves already there?
No, yeah. Actually, let me show here. So here, yeah. So I do everything first in the tile 0, which is the tile where the cosmoticity is defined. So using that measure heat density model, I can predict where it's gonna be each one of the measures, which one of the galaxies will host these measures. So I choose these host galaxies here, and then when I choose their positions, I mean their redshift, their right assumption, and declination, I can then sampling the mass of the binary, the angles, the spins, everything necessary to have the inputs in the waveform functions. So first of all, I sampling all the gravitational wave parameters, that 15 parameters for each event. Then I save this in a file, and then I put in the waveform function.
So you first pick a galaxy from the probability that you show,
Yeah,
and then based on the properties of this galaxy, you sample a set of parameters for the gravitational wave that will be emitted from this galaxy. And then
yeah,
like, since you know the position and the redshift of the galaxy, that's already fixed.
yeah. In principle, only the position of these events is correlated with the galaxy itself, because here the measure height density depends on the mass of the galaxy. So I take a galaxy or a cluster of galaxy and calculate the measure heat density in that region. For example, I calculate and give me in 10 years that's gonna happen 5 measures there. Then I take these 5 measures and distribute on these galaxies here.
Yeah, well, the distribution of this parameter is the same for all galaxies, is it? The distribution of these 15 parameters is the
Yeah,
same.
yeah.
That was your question, right? So they just wait, the galaxies are just weighted according to this plot. No? So there are galaxies that are more likely or less likely. But once you identify the galaxy, the distribution of parameters. Is the
Yeah.
same.
And does the galaxy have a size, or is it like a
No,
point source?
yeah, it's a point. Yeah.
Okay. And do you find that like one galaxy can have more than one event, or is that
It's possible. Yeah.
possible?
Yeah, but it's not. It's 3.
Yeah, I mean, we don't exclude this option, but if happens, it's very difficult to happen.
In 10 years should be probability should be 10 to minus 5.
Yeah, so I mean, I didn't put any code line to exclude this option, for example, but by the probability, it's very difficult to happen.
So you do this for the first tile,
Mhm.
and so you have your catalog of galaxies and gravitational waves, and then you repeat the tile.
Exactly. Yeah.
And then you sample from the same distribution, but the different sound.
Yeah.
Let's go.
Yeah. Different realizations of the same statistics. Yeah.
Anyway, you will be here. You're leaving tonight?
Yeah.
When
Yeah. I'm gonna stay all
you apply this at 8? When do you have to leave from here?
I didn't see my flight time, but I think it's at night. Yeah.
Okay, so you will still be here for most of the afternoon.
Yeah. Sure.
Okay, let's thank Rania again. So we take a short break. So we reconvene in 7-8 minutes. Take coffee with this. Okay. So at 15 past, now we start. Second check look at time. Es como lo de si puedo inventar.